Hello, welcome back. So this is the review of the lecture from last week. So we started with basis functions, and the motivation was that not every classifier or classification problem can be solved by a linear classifier, and this is the famous so-called XOR example, where you want to have class 1 at the input location 0, 0 and 1, 1, and you want to have the response -1 for the input pattern 0, 1 and 1, 0, and no matter how you move this hyperplane, you will not be able to separate these data points. And the trick is to add additional inputs, or more abstractly to define basis functions or feature functions. So in this case, the problem can be solved if we add this additional input, which is formed from the original input. So it's the interaction term for x1, x2, and then we can define a function which exactly goes through these data points. And you see from initially 2 dimensions, we went up to 3 dimensions. So in 3 dimensions, with this way of defining the third basis function, so phi naught would be the constant minus 2 phi 1. So phi 1 of x would be the first basis function. Phi 2 of x is equal to x2 would be the second basis function, or the third basis function, and phi 3 here be the third basis function. Okay, so this is 0, 1, 2, 3, so this is third basis function, x1 times x2, and so they are, in a way, the new inputs to a linear classifier, and the goal is to learn the weights on these classifiers, on these inputs, on these basis functions, sort of. So these are is another layer on which we apply now the linear classifier, and we learn the weights 1, -2, -2, 4. And the same issue occurs in regression. So not every function is a linear function. So here's a typical example of something which might be linear for small input values, so around 0, but then sort of saturates. So that's a very common behavior. And again, by using basis functions, in this case the constant x, x2, x3, we can approximate this blue function quite well with the appropriate weights. And it turns out 2 of the weights are 0, so we only need the constant and the third order term here, and then we can nicely fit this function, these terms. Very common basis functions are these polynomial basis functions, which are formed by the original inputs and then by products, and then higher order products of the inputs. And if you want to look at it as a network, we have inputs here, x1 to xm. Then the basis functions calculate their responses, and then we form a linear system to do the prediction. Also a linear function can be written as basis functions, where the basis functions would be then individually tuned to the individual inputs, but you can also look at them as a basis function system. Then the issue is how to train the weights. So now the weights are between the layer of basis functions and the outputs. Same here. And so the important thing to recognize is that after the transformation into the space of basis function, everything becomes a linear problem again. So we can use linear regression or a linear classifier to train these weights. so the key is to replace these the design matrix of the axis, the original inputs, by the design matrix of the activation of the basis functions. So y stays the same. So essentially these terms here, these matrices change, because before they were x, now they are phi matrices. But the equations, as you can see, are exactly the same as before. So that's, in a way, it's simple, but maybe a little bit difficult to understand completely initially. So another popular set of basis functions are the radial basis functions, or RBFs, which have this Gaussian shape. So they have a center, that's this term over here, and then a width, which is this parameter over here. And then they have this local behavior, and they have a center of highest activity, and then they drop off to both sides. Or in 2 dimension, now here we draw the center of the basis function and sort of the equipotential here. So they have this roundish behavior if you cut them somewhere. And with only 3 basis functions, we can plot model pretty complicated functions, as we show over here. So the blue ones are given. These are Gaussians with centers we picked appropriately. We only have to learn the output weights, and by learning weights on these blue basis functions, we can model this pink function here quite nicely. And if you look how the input data looks in, so here are the input data. Here we have the non-separable classification problem. Here should be green, then red, then green class. If we use these 2 basis functions and we look in basis function space, so now we're looking, so this is the activation of the first basis function, this is the activation of the second basis function. We see that the data is still on a one-dimensional space, a one-dimensional manifold. So the dimensionality of the data doesn't necessarily increase, although it now lives in a 2-dimensional space. But in this 2-dimensional space, it's very easy to separate these 2 classes. So that's also an interesting way to understand what's going on. In particular, later on when we discuss a lot on the meaning of manifolds. So this is the one-dimensional case, but if you look in the phi space and look at the activities of the basis function, the data is really on this manifold. Then there's an issue of what is the optimal number of basis functions and how many do we really need. So here is a plot, and you see, if you think in a problem with 1 input, maybe we need 10 basis functions, and we can model a class of smooth functions. If you want to have the same smoothness as in 2 dimensions, you already need 100 basis functions. So the required basis functions sort of increase exponential. And this is the famous curse of dimensionality we have to address. So we need to find ways of doing finding the right basis functions efficiently. And there's some forward selection, backward selection are 2 options we can do. Here was an example. Okay, so that was a lecture on a review on the lecture of basis functions. And as you, my message would be, hopefully you see how simple it is. It's a transformation from input space to some basis function space. And the basis functions can be defined in different ways. And then in this basis function space, everything is a linear problem again, and we can apply our learning rules for linear systems. But the consequences are quite severe, and it's now a much more powerful system. We can solve nonlinear classification problems, nonlinear regression problems, and to do this in the right way is sort of a big part of what is going on in modern machine learning. So the second presentation was on an introduction to function approximation for machine learning. And so the question is, the issue is shown over here. So the space of all possible functions is enormous, and in general, or in particular for a special application domain, the functions, so the classifiers or the regression models, come from a very small part of that space. And it's important that our model class sort of fits the target class quite well to have a chance to learn the function and to be also efficient at learning this function. So this is one way to plot it into a Venn diagram. So here we have our function class, T. So it displays a set of functions, and this is the model class. So it might be another class of functions. For example, this could be all neural networks with a certain number of hidden layers, or a certain type of RBF network. And then there might be some overlap, so some elements of the target function class which can be perfectly modeled by an example from the model class. So then we can perfectly learn the map with enough data points. But sometimes there is a discrepancy, so there are some functions in the target class which cannot be modeled very well. But this error should be small. The approximation error between the in the worst case, so the worst sort of target function, and the best one of the model class, this distance should be small. And that's an issue in approximation theory to analyze the behavior of its epsilon. This maybe is a more typical example. So the target function class is larger than the model function class, and we want to have a model class where this, in the worst case, this epsilon is small, the distance between the worst case function in the target class and then the best fitting one in the model class. There are also statistical issues, which is not so much the focus of this lecture. So how many data points do I need that I can identify the best element in the model class? So with finite data, I might think this is a good model, and only if I have more and more data, I will converge to the best possible element in the model class. And in our case, we say it's characterized by a weight vector. Or in this case, the target function is part of can be realized by one element of the model class. So, but still, with not enough data, we will not know which one that function is. So there will be this also the statistical error. And to a first approximation, one should think that the total error is the sum of them. So here it's just a statistical error. In this case, it would be the statistical error plus the approximation error. And there are other more practical issues: computational complexity, memory complexity, and so on. So we need to define what we mean by close, and one definition is we take the difference between two functions, take the square of that, and integrate them over some unit ball, and maybe divide by the size of this ball. So we call it sometimes dist sub b. So in that term, we want to have epsilon to be small. So the worst case, the distance between a function from the function class, target class, and the model class should be small. We can also define a weighted distance where we also use this p of x, which is sort of like a probability distribution. So it should be a function which is non-negative and should integrate to 1. So here we can emphasize that some input data points or some input data regions are more important than others. And this is important if we consider that the input data is really on a submanifold. Yeah, so we did this analysis before that if in one dimension we would use A RBFs, then in m dimension we would need a to the power of m real basis functions, so the required number of basis functions sort of goes up exponentially with the dimension. So this was a picture we already looked at. And typically we use this order of notation because there are a lot of maybe constants in front we don't want to care about right now. So the first analysis would tell us the number of basis functions we need is sort of the order of the number of basis functions per dimension to the power of the dimension, because we have this exponential increase. Oh, this is for me, just sorry. So in a second analysis of dimensionality, so this is so here we say the approximation error if we just change these equations. So epsilon is on the order of so the approximation error 1 over a to the power of m. M is the set of all functions with m inputs with continuous partial derivatives up to order m. So m sort of tells us a little bit about the smoothness of the functions in the target class. And if we make this assumption that the approximation error can be written in this way, we get this formula. So the number of required basis functions is on the order of 1 divided by the error we want to tolerate to the power of number of inputs divided by the smoothness parameter. And if you want to read up on it, it is discussed in this paper. So if we maybe are able to tolerate 10% error, then the number of basis functions is 10 to the order of m divided by m. And if this becomes a big number, then this is really impossible. And this is the curse of dimensionality. And so and it depends on this, the number of inputs divided by the smoothness parameter. So if m is large and large m is large and small m is small, so we have non-smooth functions in high dimension, then we really have this curse of dimensionality, and m phi increases exponentially with the inputs. So that's really impossible for anything. If m is small, so the input dimension is relatively small, but the complexity might be high, so the smoothness is small, then we can use this trick of projection or transformation in basis function space, and then we still can get away with maybe a reasonable number of basis functions. And since we essentially blow up the dimensionality by going from m to m phi, I call this the blessing of the dimensionality. So we can solve even complex problems if the input space originally is low dimensional. Of course, m is large, so the inputs can be large if small m is also large, so we have a high degree of smoothness. Then we can tolerate maybe quite large input dimensions, so maybe even up to 10,000 inputs. And then, of course, the triple one is a small input dimension and a large smoothness, which is very easy to solve. Fortunately, for case 1, which seems so terrible, there are even special cases where we can still have a chance of solving it. And the first one is 1a, so this is the null network case. If we are, if in reality a lot of the M5 basis functions which we really would need have 0 weight, so the solution is sparse, only a very small number is really needed in the approximation, and we have a smart way of finding these much smaller number of basis functions, then we can also beat the curse of dimensionality, and this is really what's going on in null networks. Then another special case is if P of x, so the input data distribution, is really on a low dimensional manifold, then we can exchange this, and instead of using M, we can use MH, so the dimensionality of this subdimensional manifold, and MH to divide by M might still be reasonable when M divided by M is already out of reasonable numbers. So here's an example. The data is really on the submanifold, so the input dimension is really in a way 1, so the degrees of freedom is 1, and not, although the input data lives in this two-dimensional space x1, x2. Or if this distribution is not on a linear space, then it's called a nonlinear manifold. So manifold also indicates that this is sort of smooth here. And then we discuss why nature, with the same argument as before, might be often calculating this manifold data. One issue is in reality we can also in the test phase be off the manifold, so we might have test data which are not on this manifold, and then the performance might really decrease drastically in this case when the training was dependent on the fact that it was on the manifold, and this is one example of these, or one explanation for these catastrophic examples where you show whatever, some object like a monkey, and then you change some pixels in moving away from this manifold, and you don't even see it, but now it's classified as something completely different. You've probably seen some of these examples in the press. So the critical factor is the number of inputs divided by the smoothness. So if this is too large, we have case 1, and that's difficult, but there are still special cases. One was when when it's a very sparse solution, so many basis functions really have 0 weights. The second one is if the data is on the manifold, we can replace M by MH. And the third one is this composability, which we'll discuss in the lecture on deep learning. So hopefully that gave you some insight. I think although we didn't use much math, I think the analysis is quite meaningful and deep, and explains really a lot about why neural networks work, why deep learning works. All of this can be analyzed in a more mathematical way, calculating bounds and being very precise about certain things, but that really becomes a very complex mathematical enterprise endeavor where you have to have a lot of skills, and we could spend probably several lectures just on this. But I think the critical understanding I try to provide already with this lecture. Well, thank you very much.